Out there, in the absolute and unforgiving blackness, time itself behaves differently. The void between galaxies is a tapestry woven from distance and the constant, unrelenting speed of light. To look out into this expanse is not merely to look across space, it is to look backward into the deepest corridors of history, to an epoch so remote it defies human comprehension. For 13 billion years, light from the universe's infancy has been journeying, its waves stretched and fatigued by the expansion of space-time itself. This ancient, weary light carries a story, the genesis of everything we see. And now, for the first time, we have built an eye capable of reading its faint, whispered script. 1 million miles from Earth, a golden honeycomb drifts in the silent dark, shielded from the glare of its own home star. This is the James Webb Space Telescope, humanity's most ambitious sentinel, an infrared oracle designed for a single profound purpose: to witness the cosmic dawn. Its 18 hexagonal mirrors, coated in a gossamer layer of gold, work in perfect unison, a colossal bucket designed to catch the faintest, oldest photons in existence. For months, it has been staring into a patch of sky that appears utterly vacant to the naked eye, a region of profound emptiness. But Webb sees differently. It perceives the universe in wavelengths of light invisible to us, the very colors of creation. In the quiet hum of a data processing center back on Earth, a team of astronomers watched as the first images from a new deep field survey were stitched together. They were looking for the faintest, reddest smudges imaginable. These would be the seeds of today's majestic galaxies, the first chaotic nurseries of stars, igniting in the primordial gloom. One by one, the candidates appeared, faint and small, just as theory predicted. But then, something else materialized from the digital noise. An object designated with the unassuming catalogue number, 25P Nu 39. It was a smudge like the others, but it was different. It was too bright. It was too clear. And as the spectral data began to stream in, a quiet disbelief rippled through the control room. This was not some faint, embryonic proto-galaxy. The light from 25P Nu 39 told a story that was, by all accounts, impossible. It was a ghost from a time when such beings were not meant to exist. The data suggested a galactic metropolis, a sprawling city of stars, shining in the universe when it was a mere toddler, less than 300 million years old. This is the equivalent of finding a fully formed, functioning skyscraper in the archaeological strata of the Stone Age. It was an anomaly, a paradox written in starlight, a discovery that didn't just add a new chapter to our cosmic history books, but threatened to tear the entire volume to shreds. The impossible galaxy, 25P Nu 39, had just been discovered, and with its silent, ancient light, it brought a crisis to the very heart of cosmology. To truly grasp the magnitude of this confounding discovery, we must first appreciate the revolutionary instrument that made it. The James Webb Space Telescope is not merely an upgrade to its predecessor, the venerable Hubble. It represents a fundamental shift in our ability to perceive reality. Hubble, a legend in its own right, gave us our first crystal-clear views of the cosmos, but it was primarily an eye for visible light, the same narrow spectrum our own biology evolved to see. It was like trying to understand the full richness of a symphony by only listening to the violins. Hubble could see the grand, mature galaxies, but the universe's earliest moments, its opening chords, were shrouded from its view. The genesis of the cosmos is a story told in infrared. Imagine standing on a harbor, watching a ship sail away toward the horizon. As it recedes, its details fade, and its colors seem to wash out. Now, imagine the universe itself is the expanding ocean. A galaxy born in the early cosmos emits brilliant, blue-white light from its first massive stars. But as that light travels for billions of years across an ever-stretching fabric of space-time, its waves are pulled, elongated, and shifted, much like the sound of a receding ambulance siren drops in pitch. This cosmological redshift pushes the brilliant, high-energy light into the lower energy, longer wavelengths of the infrared spectrum. The cosmic dawn is forever invisible to human eyes. To see it, we needed to build an eye that could perceive this cosmic heat signature. Building such an observatory was one of the greatest engineering challenges humanity has ever undertaken. Its primary mirror, over 21 feet across, was too large to fit into any existing rocket. So, it was designed like a piece of intricate origami, a golden flower that would have to unfold itself flawlessly in the vacuum of space, a million miles from any helping hand. Each of its 18 beryllium segments, chosen for its lightness and stability at extreme cold, had to be polished to a precision measured in atoms and aligned with nanometer accuracy. If this mirror is the telescope's eye, its sunshield is its very soul. A 5-layered, kite-shaped membrane the size of a tennis court, it is an extraordinary feat of thermal engineering. It separates the observatory into a hot side, facing the sun, and a cold, dark side, where the scientific instruments reside. The temperature difference it maintains is staggering, from a scorching 85 degrees Celsius on the sun-facing layer to a mind-numbing minus 233 degrees on the instrument side. This extreme cold is not a luxury, it is an absolute necessity. Webb is so sensitive to infrared that its own heat would blind it, drowning out the faint whispers from the dawn of time. This marvel of engineering was then launched and sent on a month-long journey to its final destination, the second Lagrange point, or L2. This is a special, gravitationally stable location in space, a cosmic parking spot where the gravitational pulls of the Sun and the Earth balance perfectly. Here, Webb can orbit the Sun in lockstep with the Earth, keeping its vital sunshield always pointed at the Sun, Earth, and Moon, ensuring its delicate instruments remain in perpetual, frigid shadow. It is from this lonely, silent outpost that the Golden Sentinel began its work, turning its gaze toward a tiny, dark patch of the sky in the constellation Ursa Major and waiting patiently for photons that began their journey when our own planet was nothing but dust and gas. The first signals from 25 Pnu-39 were unassuming, just a collection of pixels in a vast digital image, but it was Webb's specialized instruments that transformed this faint smudge into a cosmological crisis. The real revelation came not from the image itself, but from its spectrum. Using an instrument called the near-infrared spectrograph, or NIRSpec, astronomers performed a kind of cosmic autopsy on the galaxy's light. Spectroscopy is the science of breaking light down into its constituent colors, its fundamental frequencies. Much like a prism separates sunlight into a rainbow. Every element, every atom in the universe absorbs and emits light at specific, unique wavelengths. This creates a pattern of bright and dark lines in the spectrum, a kind of celestial barcode. This barcode is the astronomer's Rosetta Stone. It reveals a staggering amount of information: the object's chemical composition, its temperature, its density, and, most critically, its distance. As the team analyzed the barcode of 25 Pnu-39, the first number they calculated was its redshift. The result was breathtaking. The lines in its spectrum were shifted so far toward the red end that it placed the galaxy at an era just 290 million years after the Big Bang. The universe at this point was less than 2% of its current age. This was the heart of the cosmic dark ages, a time when the first stars were just beginning to puncture the primordial hydrogen fog. To find any galaxy here was a triumph. But the subsequent data transformed triumph into sheer bewilderment. From the galaxy's brightness, the team could estimate its total stellar mass. The number that came back seemed like a computational error. 25 Pnu-39 appeared to contain over 100 billion stars. It was a stellar metropolis, a galactic behemoth on par with our own Milky Way's spiral arm companions. This was utterly, unequivocally impossible according to our established models. Think of galaxy formation as a process of building with Lego bricks. The standard cosmological model says that in the early universe, you only have the smallest, most fundamental bricks available, tiny clumps of dark matter and gas. Over immense stretches of time, these small bricks slowly collide and merge, gravitationally attracting one another. Two small clumps form a slightly larger one. That larger one pulls in another, and so on. It is a slow, hierarchical process that unfolds over billions of years. First, you build small structures, then medium ones, then the grand, sprawling Lego castles like our Milky Way. What Webb had just found in 25P Nu 39 was a fully assembled, intricate Lego castle sitting in the box moments after it had been opened. There simply hadn't been enough time for it to be built, brick by agonizing brick. The paradox deepened with the analysis of its chemical composition. The spectral barcode showed strong signatures of elements like oxygen, nitrogen, and carbon. In astronomical parlance, anything heavier than hydrogen and helium is called a metal. But these metals are not created in the Big Bang. They are forged in the nuclear furnaces of stars and can only be released into the cosmos when those stars die in spectacular supernova explosions. To have such a significant abundance of these elements in a galaxy so young meant that it must have already gone through multiple generations of star birth and death. Massive, first-generation stars must have formed, burned through their fuel at a furious pace, exploded, and seeded the surrounding gas clouds with heavy elements. Then, a second generation of stars, rich in these new metals, must have formed from that enriched gas. This entire, frantic cycle of creation and destruction had to have occurred, at a rate and efficiency far beyond anything our simulations had ever suggested was possible. The galaxy was not only impossibly large, it was impossibly mature. It was chemically ancient at the dawn of time. The final piece of confounding evidence came from the imaging itself. While still a distant object, Webb's unparalleled resolution hinted at structure. It wasn't just a chaotic, disorganized clump of gas and stars, as one would expect from the violent early universe. There were suggestions of a central bulge, and perhaps even a nascent disk. It was organized. Gravity and angular momentum had already begun to shape it into a coherent, rotating system. This kind of organization takes time, eons of gravitational settling that 25P Nu 39 simply did not have. The evidence was overwhelming, and every new piece of data only sharpened the edges of the paradox. The team checked their calculations, they reran the models, they searched for any alternative explanation. Could it be a closer object masquerading as a distant one? The unambiguous redshift data made that impossible. Could the instrument be miscalibrated? All other objects in the same field of view behaved as expected. The inescapable conclusion was that 25P Nu 39 was real, and its existence posed a direct, profound challenge to our entire understanding of how the universe grew up. The standard model of cosmology, known as lambda CDM, has been the bedrock of our cosmic understanding for decades. It is a remarkably successful framework that explains a vast range of observations, from the cosmic microwave background radiation to the large-scale distribution of galaxies. The lambda refers to dark energy, the mysterious force causing the accelerated expansion of the universe. The CDM stands for cold dark matter, an invisible, non-interactive substance that is believed to make up about 85% of all matter in the cosmos. In this model, it is the immense gravity of cold dark matter that provides the scaffolding for structure to form. After the Big Bang, the universe was almost perfectly smooth, but there were minuscule quantum fluctuations, tiny variations in density. Dark matter, being immune to the outward push of radiation pressure, began to clump together in the slightly denser regions. These clumps became the gravitational wells, the seeds into which ordinary matter, hydrogen and helium gas would later fall. This process is fundamentally bottom-up. The smallest dark matter halos form first, creating the gravitational cradles for the first dwarf galaxies. These dwarfs then merge over cosmic timescales, their stars and gas mixing, their central black holes combining, building up ever larger and more massive galaxies. Our own Milky Way is a testament to this history, a product of countless galactic mergers over 13 billion years, we can still see the shredded remnants of smaller galaxies it has cannibalized, long stellar streams that orbit our galactic core like ghosts of past victims. The Lambda CDM model has been tested and verified countless times. Its simulations, run on the world's most powerful supercomputers, produce a universe that looks remarkably like the one we observe around us today. But they do not, under any standard set of assumptions, produce anything like 25P nu 39. It is an outlier of such extreme proportions that it cannot be dismissed as a statistical fluke. The existence of this single, ancient object acts like a colossal wrecking ball, swung at the elegant edifice of hierarchical structure formation. It suggests that in the early universe, the process of building galaxies was not a slow, patient accumulation of small parts. Instead, it seems something allowed for massive, monolithic collapse. The universe, it appears, was capable of building its skyscrapers first. This single data point from the Webb telescope forces us to ask a terrifying and exhilarating question. Is our fundamental model of the cosmos wrong? Or, at the very least, is it woefully incomplete? When the initial paper on 25P nu 39 was published, the astronomical community was thrown into a state of vibrant turmoil. The first reaction, as is proper in science, was deep skepticism. Rival teams reanalyzed the public data, searching for flaws in the initial team's methodology. They looked for exotic explanations. Could there be some unknown foreground object whose light was being gravitationally lensed by an intervening galaxy cluster, making a small background object appear artificially large and bright? While lensing is a real phenomenon, the characteristics of 25P nu 39 didn't fit the profile. There was no telltale distortion or multiple imaging that lensing would produce. Gradually, as other early universe candidates with similarly challenging properties began to emerge, from other Webb deep field surveys, the skepticism began to shift toward a grudging acceptance. The data was real, the paradox was real, the crisis was here. This is not a moment of failure for science. On the contrary, it is the very essence of the scientific process. A theory is only as good as its ability to explain observations. When an observation emerges that fundamentally contradicts a theory, it is a gift, an opportunity to push beyond the boundaries of our knowledge and discover a deeper truth. 25P nu 39 has shattered the comfort of our established models and thrown open the doors to a new frontier of cosmic inquiry. The world's theorists are now scrambling, proposing bold and sometimes radical new ideas to explain how a galaxy could grow so big, so fast. One of the most compelling, if unsettling, ideas involves something called primordial black holes. Our standard model assumes the seeds of galaxies were tiny quantum fluctuations in density. But what if the universe was seeded with something much more substantial from the very beginning? Some theories suggest that in the chaotic, ultra-dense conditions of the first second after the Big Bang, regions of matter could have spontaneously collapsed under their own gravity to form black holes, not from dying stars, but directly from the fabric of space-time itself. These primordial black holes could have come in a range of sizes, some as massive as 100,000 suns. If they existed, they would have been phenomenal engines of galaxy formation. They would act as pre-existing, hyperdense anchors, their immense gravity immediately and rapidly pulling in vast reservoirs of gas from their surroundings. Instead of a slow, bottom-up process, this would be a get-rich-quick scheme for galaxy building. A massive primordial black hole could have seeded a behemoth like 25P nu 39, jump-starting its growth and allowing it to reach an impossible size in a cosmic blink of an eye. Webb may have inadvertently found the first circumstantial evidence for these long-theorized, elusive objects. Another avenue of investigation focuses on the universe's very first stars, the so-called population 3 stars. We have never directly seen these stars. They were born from pure hydrogen and helium and are thought to have been titans, hundreds of times more massive than our Sun. Because of their immense mass, they would have burned through their nuclear fuel with unimaginable ferocity living for only a few million years before exploding as colossal supernovae. Perhaps our models of these first stars are too conservative. What if they formed in much denser, more numerous clusters than we thought? What if their explosions were far more efficient at creating and distributing heavy elements? It's conceivable that a supercharged burst of population 3 star formation could have rapidly enriched and energized the gas in the early universe, allowing the next generation of stars, and thus the galaxy itself, to form at a pace that seems reckless by our current standards. 25P, Nu 39, might be the signature of this initial, incredibly violent phase of cosmic creation, a process more akin to a wildfire than a slow smolder. A more fundamental revision might be needed in our understanding of the universe's most mysterious component, dark matter. We call it cold dark matter because we assume its particles move slowly, allowing them to clump together easily into the small halos that kickstart bottom-up formation. But what if it isn't so cold? Theories of warm or fuzzy dark matter propose particles that are lighter and move faster. These properties would suppress the formation of small-scale structures, favoring the collapse of much larger, more diffuse clouds of gas from the outset. This could naturally lead to the formation of massive galaxies first, a top-down scenario that would elegantly explain the existence of 25P Nu 39. Finding evidence that challenges the cold nature of dark matter would be a revolution, not just in cosmology, but in fundamental particle physics, opening a window into an entirely new sector of nature beyond the standard model. The James Webb Space Telescope was built for exactly this moment. It was designed not just to take pretty pictures, or to confirm what we already suspected to be true. Its primary mission, its deepest purpose, was to find the things that don't fit, to uncover the anomalies that break our theories. Because it is only at these breaking points, in these moments of profound confusion, that true progress is made. 25P Nu 39 is not an answer. It is a question, perhaps the most important question in cosmology today, and Webb is just getting started. As it stares deeper and for longer, it will find more of these impossible structures. It will map their distribution, study their stellar populations in greater detail, and provide the crucial data that will allow theorists to distinguish between these competing new ideas. We are standing on the cusp of a paradigm shift, a moment in history, akin to when Galileo first turned his telescope to the heavens and shattered the old geocentric model of the universe. The story of 25P Nu 39 is more than just a scientific puzzle. It is a profound lesson in cosmic humility. For centuries, we have crafted a story of the universe with ourselves as its thoughtful, intelligent observers. We built a model, Lambda CDM, that was neat, orderly, and predictive. We grew comfortable in our understanding of a slow, methodical cosmos. But the universe, it seems, is under no obligation to conform to our expectations or our timelines. It is wilder, more creative, and more complex than our models had allowed. It appears to have been in a furious hurry to build grand structures, to forge the elements of life, and to set the stage for the cosmic drama that would follow. This single, faint, red smudge from the dawn of time has forced us to reconsider our place in that story. It reminds us that our knowledge is a small island in a vast ocean of ignorance, and the purpose of science is not to forever defend the shores of that island, but to build ships and set sail into the unknown. The James Webb Space Telescope is our flagship, and it has just sent back a dispatch from a truly new world, one that operates by rules we are only just beginning to decipher. The impossible galaxy is a signpost, a beacon shining from the edge of time. It tells us that our neat and tidy origin story is about to be rewritten. The universe is stranger, more magnificent, and more surprising than we ever dared to imagine. And our quest to understand it, the greatest intellectual adventure in human history, has just entered a new and exhilarating chapter. The search continues.